Just a little context for this talk. I'm not a lawyer, but I sit at a law school now as a postdoc, and I'm often in the room with lawyers. And so the context for this is what is like a growing consensus among sort of privacy scholars in the U.S. that there's something wrong with the current regulatory system for data protection in the United States, especially. This is sort of in the wake of new European rules that are shifting some of the standards of how personal data is treated sort of globally. And so this is really intended, this work is intended to be part of that conversation. I feel like it was set up well by the kind of works in progress papers from yesterday. But also there's hopefully a compelling technical claim at the core of it that I hope has sort of wider use, maybe in some of the security contexts that seem to be more the bread and butter of this conference. So that, I'd like to talk about three motivating examples, and I'm going to try to argue that they all have something in common, though they're from quite different settings. So this is an old chestnut from the privacy scholarship literature. So Target, the retailer, at some point discovered that buying certain products, such as scent-free hand lotion, correlates in a kind of non-obvious way with pregnancy and childbirth. And they started sending coupons to people based on this inference. You know, someone would buy certain products, and they'd send coupons for, you know, baby stuff. And in one version of the story, they sent coupons to the house of some young woman, and this is how her family learned that she was pregnant, and this is quite alarming. And so since then, Target has learned to mix the coupons for baby-related stuff with other sorts of coupons in order to dilute that signal to make it less noticeable. But that was an example of a kind of data-related privacy violation that people used for some time. Since then, there's perhaps a more pressing example of this, which is that researchers have showed that a lot of sensitive and private attributes, including political views, ethnicity, sexual orientation, and especially psychographic profiles, can be inferred from social media activity. And so allegedly, this social media data has been used to create psychographically targeted advertising based on personality traits that were never intentionally revealed by the users. And then as a third example, a journalist, I think it was like Quartz, or discovered that a smart provider, in this case was Google, the smartphones are collecting the identity numbers of the cell phone towers that the smartphone was connecting to, even when users had disabled location tracking on their device. And what the journalists were saying is like, well, you know, the cell phone tower IDs are really good proxies for smartphone location, and so the argument was this is a violation of the user's expectations that location would not be tracked. And they put pressure on Google, and Google says they've stopped collecting that information or storing it. So what's going on with these examples? I'd say that the issue is that in each case there's an unintended semantics to information that was shared. And that's surprising from a privacy perspective. So I'm drawing from contextual integrity, which is a framework for understanding privacy that has come up in a couple other talks. Contextual integrity, developed by Nissenbaum, says that privacy is a matter of appropriate information flow, where appropriateness means in accord with norms, and those norms, according to the theory, can be expressed in terms of sort of actors involved, who's sending the information, who's receiving the information, who is the subject of the information, transmission principles such as confidentiality and reciprocity, and then the information topic or attribute, what the information is about. So for example, patients are expected to give data about their health or information about their health to their doctors under the condition of confidentiality. It's an example of an information norm, right? And the problem is that contextual integrity does not do a super good job of dealing with the kinds of examples that I just talked about, because the topic is somehow unanticipated by the people involved in the data transfer. And there's some prior work under the heading of origin privacy done by Nissenbaum, myself, Michael Shantz, Peter Marsdale on Palm Data. And we basically arrived at the conclusion that it's really hard to know what topics information is not about. They're trying to put, and then this research follows up on that, trying to put more meat on that statement. The paper also contains a survey of data protection regulations that are like international ones, US federal and state, and European, and one of the very helpful reviewers said I shouldn't focus on that for the talk, so you can check it out in the paper. But just as a summary, lots of different regulations refer to data or information moving or changing hands in various ways. So there's a sort of general sense of people, okay, information is flowing, but not all refer to particular topics of information. It seems like a particularly recent trend, the European GDPR and the new California law, both have stipulations saying that data processors have to reveal to data subjects what categories of information they store about those people. So this kind of categories term gets used for the sort of semantics of information. And that seems to be trending as new data protection regulations come in. Probably the most interesting thing that came out of the survey is that COPPA, the Child Online Privacy Protection Act, is actually quite special in that they have this clause conditioning on whether an operator either directs a service at children or has actual knowledge that a child is a user. And we'll get back to why that's an interesting condition later. But the main conclusion of all this is that there's this intuitive idea of information flow in both social theory of privacy, as in contextual integrity, and also in these regulations, and it's this idea that information flows kind of like a fluid from here to there, and it carries meaning with it as it goes. And the problem is this intuition is not very accurate. It's violated by these sort of unintended semantics cases. And my argument is that the physics of information flow in this sort of sense is actually quite different from what this intuition would suggest. And it's important to have a good model of how information flows in these contexts that is both intelligible to people like lawyers and hopefully the general public, and also is rigorous enough for engineers to use in their applications. So this is what I'm proposing. What I'm suggesting is we start with contextual integrity's appropriate information flow framing, but then really ask, well, what is information flow? I'm going to draw on a philosopher, Fred Dretske, who wrote a book called Knowledge and the Flow of Information and proposed a definition, I think in the early 80s, and then formalize that theory in terms of Bayesian networks and Pearl's theory of causation to make it more computer science friendly and sort of update it for today's rigor. And because we need to give it a name, let's call it situated information flow theory, or SIFT for short, and there's some policy implications that follow from it, and the claim, totally untested, but we can argue about it, is that this is going to be useful for both policy people and engineers if it's ever applied. So here's an example to kind of get the intuition pump. So Alice is teaching a class and has determined the students' ranks, who's first in class, who's second in class. And Alice sends a message to Eve saying, Eve, you're the first in the class, privately. And she's telling this to every student. Now, Eve can now infer something about Bob's rank from hers, because she knows the structure of the situation. So did information about Bob flow to Eve or not? Well, here's the philosophy bit. So Fred Dretske, who's explicitly building on Shannon, information is a naturalistic and a causal property. It's something that is in the world. It's a measurable natural phenomenon. And for Dretske, the information, that P, is that signal or message that's needed for a suitably equipped observer to learn P due to the nomic associations of the signal with P. The tough term in this is nomic associations. That means sort of law-like or regular, right? And so, for example, like a red light carries information that the train is coming because regularly, lawfully, the light is red if and only if the train is coming. So these nomic associations between a signal and what the signal is about are what make that signal information, that P. And I gotta say, pace to the prior computer scientist's definition of information flow. There was a great review that pointed out that there's lots of good work on that in like programming language security. This is just a different terminology, but we can talk in the questions about sort of how they're related. It's an interesting point. So how can we work with this definition from Dretske? I expect this is a recap for many of you, but let's talk about Bayesian networks. You get a directed acyclic graph of nodes. Each node represents a random variable. Each random variable has a conditional probability distribution based on its parents. And if you combine those conditional probability distributions together, you get a joint distribution over all the random variables, and it's a succinct representation of that system. And there's some really nice properties of Bayesian networks. One is that you can qualitatively read off independence relations from the graphical structure. So association or dependence, in a sense, flows through the graph, but not just in the direction of the arrows. A causes B. There can be a probabilistic dependence between those variables. But there can also be a probabilistic dependence between two variables that have a common cause. And you can also have a probabilistic dependence between two variables that have a common effect that is observed. So, so for example, in the common cause case, you had Alice giving the ranks to the students. The common effect case is a little trickier, but say my wife and I, we're the only people that check our mail in the morning. If I know that the mail has been checked and I didn't do it, it meant she did it. So one other useful thing about this representation that makes it causal is the do operation. It's proposed by Judea Pearl. You can imagine that as sort of an intervention, an exogenous intervention on the model. So say the alarm goes off if there's an earthquake or a burglary, and recessions make burglaries more likely. If you don't care about the economy and you just really want to steal somebody's cupcakes and you burgle somebody, that has no effect on the economy, even though it will set off the alarm. So the semantics of that do operation is that it essentially cuts off the prior, the parents of the node that's intervened on, and leaves the downstream distributions unchanged. And that's important mainly because the same joint probability distribution can be represented by multiple Bayesian networks, and so you've got an issue of Markov equivalent graphs kind of colliding unless you add in the semantics that makes a directionality matter. But the proposal is that we can define situated information flow as causal flow situated in the context of other causal relations. And this captures both the Dretskian intuition and is also based on the rigorous mathematics of probability. So the situated information flow gets its semantics from the nomic associations with it, where the regular associations are defined in terms of this causal structure. So let's try applying SIFT to the 3 examples from before and see whether it checks out. So say pregnancy causes purchases of some product. The store, knowing B and that relation, can then infer P. And they're associated through this direct causal relation. But if the relation isn't known, the association will be opaque. In the second example, you've got the personality of the data subject, and it causes some social media activity, and it also causes the responses to certain kind of advertisements. So if the analyst can observe M, then that tells them about R, the responses to the advertisement. So then they can pick the ads to their strategic advantage. And then the last example, say the smartphone user wants to hide their location, so they turn off their GPS, but the data subject, so the vendor still collects the cell phone tower IDs, and with that observed variable and with the locations of the cell phone towers, that tells the vendor about the location. So it's this other channel that gets association with the location. So if you're persuaded that just clarifies how these unintended semantics can come about, then there's a few implications. One, we should teach causal modeling to the lawyers. There's a lot of cognitive psychology literature that says that this kind of causal modeling is actually like a pretty good match for intuitive thinking about causal relations in the world. That's part of why it's so powerful. So the lawyers need to learn that information doesn't flow like water. It has a different physics of sort of associations depending on the causal structure of reality. And then the fact that there's some rigorous formal theory underlying it might ease the translation between policy and engineering, which would save people in my field a lot of headaches. In terms of policy design, another implication of this is that maybe we should be focusing on data transfers as a kind of default solution. Some of the policies talk about data transfer, some talk about information. Well, a lot of the new rules about revealing the categories of stored information are very well intended. That might be difficult to interpret or enforce because the question of what categories of information are or mean is nebulous. And so biasing policies toward limiting data transfers are at least less ambiguous and can be thought of formally as just the absence of a link in the network. So in cases where that is sort of trying to hit a mosquito with a cannon, like for sort of softer techniques, if you believe what I've been arguing so far, then that leaves a lot of questions unanswered, like whose model, how did they get it, how did they learn what the process was? But the implications are that the information is going the inference is going to be limited by either the conditions on the observer knowing the causal context, or the generative process that creates the data in the first place. And it's interesting that those two conditions are reflected in the Copper rule. So the knowledge that a child is a user is a statement about the observer knowledge or adversary knowledge. And the question of knowing that the service is directed at children is about the probability of the generative process creating the data. So there's a lot of interesting future work on this to do. For example, integrating this with sort of game theoretic modeling that there's a lot of awesome work on here. But this, I think, is where things need to go in terms of doing this kind of privacy regulation modeling. And there's another point, which is that in the kind of public interest literature on this space, there's a lot of concern about the opacity of sort of large-scale data processing systems with respect to sort of users or consumers' ability to understand what they're doing when they interact with them. And there's a very good article by Jenna Burrell that argues that there's 3 different sources of opacity. One might be deliberate secrecy of system operators through like trade secrecy or intellectual property of other kinds. Another might be sort of technical illiteracy of system users, just not knowing what's going on the inside of the system. And third being that the properties of the machine learning system that allow it to scale usefully. And these are all great insights, but there's another explanation for this opacity that comes out of this framework, which is that there might be a lack of knowledge about the generative process that people are in. Like if people don't know what they're revealing because they don't know, say, what personality traits are causing them to say certain things, then that could create a kind of information asymmetry, especially if those causal relations are inferable from the data when it's collected en masse. And that accords with some arguments that have been made that there are information asymmetries. Excuse me, information asymmetries at the heart of the data economy. Hopefully, there's some questions.